Hi everybody. Hi. Surinder Singh is here. Mahendra Pal, Josh, and Hina Hanan. All of you are here. Superb guys. Welcome to Momentum in Vedantu. Welcome to yet another lecture on heat and thermodynamics. Today we are going to do KTG part 2. KTG part 2. Welcome everybody. Hi. Abhyuday is also here. Superb guys. So how is everybody doing? How is everybody doing? As you can see, there is a new setup behind me. It is going to stay like this for a few days and afterwards it will change again. Okay, afterwards it will change again. But for now, this is going to be the setup. Okay, it's just temporary with what we call a temporary setup. Okay, okay. Anyways, so hi. Ayush is also here. Superb. How is everybody doing? How is Vikas stay? Hi, Vikas. I think is new. Vikas, is this your first class on this channel? I think so, my friend. I think so. I haven't seen you before. Have you seen me before? I don't know if you have. Anyways, so guys, yes. Oh, IAS after MBBS. Oh my god. Godavarti is saying that I didn't share the notes yesterday. Oh, yeah, Godavarti, if you have the link, I will share it. I will share it. Okay, if you have the link to the Google Drives, I have added the notes there, but I forgot to share the links on Telegram. I will do that. I will do that. Okay, I've added them on Google Drive, but I forgot to share the links. Okay, guys, I have three fixed folders on Google Drive. Okay, one for class 11th, one for class 12th, and the final one for the one shot videos. So I have shared the links through all the three folders. I just keep adding the folders into that. I will keep sharing the link again and again as well, but I forgot to do that yesterday. Okay. Anyways, hi Kaushik. Hi. Oh, this is Kaushik. Oh, okay. Kaushik, I will do that. Don't worry. Entertainment 2015. V Krishna is also here. Super. Sir, board आया नहीं board अभी तक नहीं आया. I'm so sorry. Board is not here. It will come. Definitely will come. Okay. Without fail, it will come. Don't even worry. Okay. Board will come. So hi everybody. Hi. It doesn't. It hasn't arrived yet. It hasn't arrived yet. Okay. Let's see if it will, but not right now. Right now it's just you and me, guys, on a laptop. Okay, studying with a vacuum tablet. Okay, so let's see how that works out. Let's first of all see if you guys can see me. Yes, you guys can still see me, guys. If you haven't shared, or subscribed to our channel, please do that. If you don't want to do that, I would suggest you that. Okay, I would suggest you that. Okay, there's no reason for you not. It's free. It's completely free for you. Okay. Hi Mahendra, I'm very good. It's a Wacom tablet. Okay, smart book. It's a Wacom tablet. Okay, very good. Okay. Anyways, guys, so let's start today's lecture. But before we start today's lecture, let's talk about the questions that I had given for homework in the last class. Once again, the person who gave the first answer is it is Surinder Singh. Okay, Surinder Singh, the correct answer first. Surinder Singh, however, I'm going to cut half a marks from you. Do you know why am I cutting half a mark from you? Okay, I'm cutting half a mark from you because you haven't written units. Okay, please, guys, remember units are important. Units are important. Do not forget about the units. Surinder, are you there, Surinder? Hi, Hina Hanan. Okay, yeah. Yeah, thank you, Jess. Thank you so much. Okay, but yeah, anytime if I was there and if I was checking your papers during that, I would have cut your marks. Okay, but online I wouldn't. But okay, please don't forget about the units. Please do not forget about the units, guys. Units are super important. Okay, all right. Next is KTG part two, guys. KTG part two. Okay. Yeah, I know Ryan Ferris, but 14 lectures are not completed. Okay, and we are well on our way to finish it within 14 lectures. So don't worry about that. Okay, let's talk about KTG part 2. So KTG part 2 is going to be the continuation of part 1 where we left up at part 1. Okay, so where we left up at part 1, guys, we talked about Maxwell distribution curve. There were three different velocities: the most probable velocity, the average velocity or mean velocity, and the RMS velocity. Okay, all of them had formulas: 2 RT by m, 8 RT by pi m, and 3 RT by m. Okay, also by the way, these formulas were also written as under root 2p by rho, under root 8p by pi rho, and under root 3p by rho. Okay, these were the formulas. You have to just remember because p by rho is equal to RT by m. where m is basically what? Molar mass of any body. Molar mass of any gas. Molar mass of any gas. I hope everybody is understood. Okay. आपके घर पर कौन रहता है? मैं रहता हूँ and मेरी family रहती है. Based on this, guys, based on this, tell me, okay, this question is by the way incomplete. Let me try to complete this. What will be the change in RMS speed of the gas on increasing the pressure while keeping the temperature constant? Okay, while keeping the temperature constant. This is a complete question, guys. Tell me the correct answer to this. Tell me the correct answer to this. I think everybody knows this. I think everybody knows the correct answer. Let's see if you can. Okay. Ayush, मेरे घर पे Hi Shravani. I will upload the notes, Shravani. Do not worry. Okay. Yeah. What will be the correct answer? Okay. Entertainment 2015 is saying A. Ayush is saying A. Fab Phoenix is also here. Oh, Fab Phoenix is saying C. Oh my God, Fab Phoenix. Why are you saying C? Huh, my friend? Why are you saying C? Oh my God. Bas Boosted is saying A. And Godavarti is saying A, and Umang is saying A, and Smart Book is saying 1. Smart Book, I don't understand that option. There's no option 1. Okay. Hina is also saying increases, and Shravani is also saying increases. Okay. Surinder Singh is saying C, 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 C. Okay, guys. Now this is where you have to pay very close attention. You have to pay 1 second. Now let me just shift this laptop a little bit to you have to pay very close attention to the two formulas which are given to us. Okay, so we are given the formula VRMS as under root 3p by rho, and that is also equal to under root 3RT by m. Now here, if you just look at the first formula, as you can see, the pressure is increasing. And if you look at the second formula, as you can see, temperature is remaining constant. If you go according to the first formula, what will you see? If you go according to the first formula, guys, you will see that the VRMS should increase, but that would be wrong. As I have told you before, this is an unreliable formula. Okay, this is an unreliable formula. When in doubt, always use formula 2. Okay, when in doubt, always use formula 2. What is, yeah, Akhil Nayak definitely knows the answer. Okay, Akhil Nayak definitely knows the answer. So what is happening here, guys? If you see here, if you go according to this formula, temperature remains constant, R is a universal constant, M is not going to change. So overall the value of VRMS should remain constant. Okay, if you look at this formula, you might think, sir, pressure is increasing, so VRMS should increase, but that is not true. Okay, if you look at the equation, Pm is equal to rho RT. If pressure increases while temperature is constant, then in that case density will also automatically increase, will also automatically automatically increase. Okay, so in this case, what is going to happen? The pressure is going to increase, guys. The density is also going to increase, and this is going to remain constant. This is going to remain constant. I hope everybody understood. If you did, please give me a thumbs up. Okay, that's why this first formula is not very reliable. You always go to the second formula, which is more reliable. We only have temperature. Okay, Fab Phoenix is correct. Surinder, very good, very good. Okay. Mm-mm. Mm-mm. Anyway, so this is the first question. The second question, again, guys, very easy question, but you will probably need to use a calculator. I will allow you to do that. Okay, I will allow you to do that. Do that. Calculate the RMS speed of nitrogen at STP. Okay, I don't know if you guys know what STP means. What is STP? What is STP? Standard temperature and pressure. Standard temperature and pressure. So what is the standard pressure? It is 1 atm. Okay, and what is the standard temperature? It is 0 degrees Celsius or 273 Kelvin. Okay, I don't know if you guys know this, but what is one ATM by the way? What is one ATM? I don't know if you guys know this. One ATM is basically equal to 1.01 into 10 raised to the power 5 Newton per meter square. Okay, in most cases, while doing calculations, at least just take it as 1 into 10 power 5. Why even bother with 0.01? Okay, so let's just take it like this. Okay. Alright, standard temperature and pressure. Very good, very good. Akhil Nayak knows the correct answer. Smart book also knows the correct answer. Hey, Akhil Nayak, it's 298 or 298? What? What? It's 298. Akhil Nayak, what you saying? Yeah, I thought it was 273. Hi Tawheed, hi, welcome to the class. How do we solve this, guys? This is once again an easy question. What we have to do is we just need to choose the formula. VRMS is equal to under root 3P by rho is equal to under root 3RT by M. First of all, you need to understand no matter which formula you use, you will get the correct answer. Okay, but I am going to use the first formula because in the first formula both values are directly given to me. This is 1 atm and the density is given as 1.25 into 10 power minus 3. The second one will also give the same value, by the way, but I'm not going to go according to that. So this will just be 3 into under root of 3 into 1.01 into 10 power 5 divided by 1.01 into 10 power 5 divided by 1.25 kg per meter cube. Okay, when you do this, guys, when you do this, this will come out of this will come out as what? Oh my God, this will come out as most probably this will come out as under root of 24 into 10 power 4 meters per second. Okay, this 1.01, by the way, I'm just considering it as 1 only. 1.01, I'm just writing it as 1 only. Okay, so it will just become 24 into this, which is very close to under root 24 into 100, 100, yes. Okay, under root 24 is very close to 5, guys. It's very close to 5, but you know what, we are just going to use the calculator. We are just going to use the calculator and we will write 24 under root. Okay, it's somewhere around 489. Okay, 4.89 into 100 meters per second. So which one do you think we should take? Which one do you think we should take? Option C or option D? Option C or option D? Huh? Option C or option D? I don't know. I don't know. I don't know. Mm-hmm. Mm-hmm. C or D, guys? C or D? C or D? I got 4.89 into 100 meters per second. Which one should I take? It will be closer to 490. Okay, it will be closer to 490. Correct, correct. Very good, very good, very good, guys. Super. Okay. So if you understood so far, let's talk about the next topic of this chapter, and that is called degree of freedom. Okay. Now, degree of freedom is what, guys? Degree of freedom is essentially defined as the total number of independent variables required to describe the position and configuration of the system. This is basically a scientific definition of degree of freedom, but yeah, in kinetic theory of gases, we also have an alternate definition. Okay, it is basically defined as the number of ways in which a molecule can store energy. The number of ways in which a molecule can store energy. Okay, what do I mean by this, guys? What do I mean by this? So let me explain this. Okay, now this little part, it's a little bit weird to think about. Okay, but just remember what I'm telling you. ज़्यादा just theory में इतना घुसो मत. Just remember what I'm telling you. What exactly is degree of freedom? So guys, in general, we have three different types of gases: monoatomic gas, or diatomic gas, or triatomic gas. Monoatomic gas, by monoatomic gas, what I mean, gases like helium and argon. There is only one molecule, there is only one atom in each molecule of the gas. Okay, now if you look at the diagram of a monatomic gas, the monatomic gases are generally going to look something like this. There is just one atom, spherical shape. Okay, now there are how many ways in which this molecule can store energy? this molecule, guys, can move in x direction and have kinetic energy due to its motion in x direction. This molecule, by the way, can also move in y direction and have kinetic energy due to its motion in y direction. And this molecule can also move in z direction and have kinetic energy due to its motion in z direction. Okay, helium is the laughing gas. I don't think helium is the मेरे पीछे दीवार पर क्या है मेरे पीछे दीवार पर क्या है oh my god what is that I don't know what is that oh tell me guys tell me what is that what oh, ah someone there no okay wait yeah anybody there you can tell me guys you can tell me I can take it I'm not afraid of okay, so what will be the degree of freedom here, guys? What will be the degree of freedom? Here, degree of freedom, by the way, is denoted by the letter F. Here, the number of degrees of freedom will be 3. Okay, the number of degrees of freedom will be 3, and these are going to be translational degrees of freedom. Why am I calling these translational degrees of freedom? Because in these 3 degrees of freedom, the molecule is having kinetic energy due to translational motion. Okay, molecule is having kinetic energy due to translational motion. I hope everybody understood. I hope everybody understood. Okay. Next, guys, is degree of freedom for a diatomic gas. If I give you an example of diatomic gas, H2 is a diatomic gas, N2 is a diatomic gas, O2 is also diatomic gas. Mostly there are so many gases which are diatomic in nature. Okay, now what exactly is the deal with diatomic gas, guys? In case of diatomic gas, the molecule can still move along. In this case they have taken this as x direction. The molecule can still move along x direction, it can still move along y direction, it can still move along z direction and have translational kinetic energy. So it will still have a translational kinetic energy if it moves in x, y or z direction. But in this case it can also rotate about this axis. Okay, it can also rotate about this axis. Basically it can rotate like this. Okay, and when it rotates like this about y axis, it can also store energy by rotating along y axis, Similarly, it can also rotate, guys, along z-axis. It can also rotate along z-axis and store energy that way. Basically, it's going to rotate like this. Okay, this one and the previous one looks the same, but basically it's going to rotate in xy plane like this. So it has two different rotational degrees of freedom as well. It has two different rotational degrees of freedom as well, because it can rotate along y-axis and z-axis to store energy. But here a natural question that comes is that, sir, it should also be able to rotate along x-axis, right? It should also be able to rotate along x-axis. And I hope everybody has that question in their mind. Now, the answer to that question, my friend, is that depends on something called moment of inertia. I don't know if you guys have heard about moment of inertia right now. Moment of inertia. Okay, if you look at its moment of inertia, by the way, is, guys, it's defined as m into r square. Okay, m into r square. If you have a mass m and it's at a distance r from the axis, the moment of inertia is defined as m into r square. Now, if you see, its moment of inertia about y-axis is not going to be zero. Why is it not going to be zero? Why is it not going to be zero? Because both the masses are a little bit away from the y-axis. Okay, so its moment of inertia about the y-axis is not going to be zero. Similarly, for the same reason, moment of inertia about the z-axis is also not going to be zero. Okay, but its a moment of inertia about the x-axis is going to be equal to 0 because the masses are already on the x-axis. So what is the distance from x-axis? Is 0. Okay, this will make much more sense when you learn what? When you learn rotational mechanics. So therefore, its rotational energy, rotational kinetic energy due to rotation in along x-axis will going to be 0 because in general the definition of rotational kinetic energy is half into I into omega square. In general, the definition of translational kinetic energy is equal to what? Half into m into v square. This is the formula everybody is aware of. In rotation, the formula is half into I into omega square. Since I about x-axis is 0, it will have 0 degrees of freedom along the x-axis. So overall, it will have 2 translational degrees of freedom and 3 translation and 2 rotation. That is it. That is it. No more degrees of freedom. I hope everybody understood this. Really hope everybody understood. Okay, now the next type of molecule that we are going to talk about is a triatomic molecule. And whenever I'm talking about a triatomic molecule, I'm talking about a triatomic non-linear molecule. Okay, so if you make a H2O gas, okay, H2O gas has one O and two H, and the angle between this covalent bond is approximately 105 and 104 degrees or something like that. This is a non-linear molecule. Okay, but if you talk about CO2, carbon dioxide, then this is a linear molecule. Now, when I say degree of freedom of triatomic, I am basically referring to these guys. I am basically referring to these guys, the non-linear molecules which are triatomic. Okay, now in this case, guys, in this case, let's say I have a non-linear triatomic molecule. So how will that look like if I look at x-axis and y-axis and z-axis? The molecule, the non-linear molecule, will look something like this. Okay, let's assume that the molecule is in xy plane. So let's just assume that the molecule what am I let's assume the molecule is somewhere around in xy plane, something like this. Okay, now in this case, if I talk about the degrees of freedom, guys, if I talk about the degrees of freedom, it has a 3 translational degrees of freedom. Why does it have 3 translational degrees of freedom? Once again, it can go along x-axis, it can go along y-axis, it can go along z-axis. So 3 translational degrees of freedom. Okay, but here it's ix, iy, and iz. All of them are non-zero. All of them are non-zero because there is some moment of inertia about each axis. Because no mass, all 3 masses are never lying on the axis. Okay, if you rotate it about this, then this mass is away from the axis, so there will be moment of inertia. If you rotate it about this axis, then these 2 masses are away from the axis, so there will be some moment of inertia. If you rotate it about the z-axis, all 3 masses are away from the axis, so there will be some moment of inertia. So it has 3 translational plus 3 rotational degrees of freedom. Now, if you did not understand anything so far, at least remember this table. Okay, what is this table? I have a monoatomic molecules, diatomic molecules, and triatomic molecules, which are non-linear. Okay, for these molecules, guys, if I talk about the translational degrees of freedom, all of them have 3 translational degrees of freedom. If I talk about rotational degrees of freedom, then the rotational degrees of freedom are 0, 2, and 3. And if I talk about total degrees of freedom, this at least you have to remember: the total degrees of freedom for a monoatomic molecule is 3, for a diatomic molecule is 5, and a triatomic nonlinear molecule is 6. At least remember this much. At least remember this much. It is super duper important. It is super duper important for reasons that will become clear in some time. Okay, for reasons which will become clear in some time. Okay, I hope everybody understood. Okay, alright. Alright, Ritik, I also want that. Please send me on Telegram. Okay. Alright. Now, next is what to do, guys. What to do? What to do? Next, we have something called law of equipartition of energy. Okay. Now, in order to understand law of equipartition of energy, you should first know something called KB. Do you guys know what KB is? KB, by the way, is called a Boltzmann constant. Okay, or I don't know if there is an A or not here. Boltzmann constant. Okay, and what exactly is the value of Kb? It's R divided by Na, where R is the universal gas constant 8.314 joule per mole per Kelvin. Okay, and Na is the Avogadro's number 6.022 into 10 power 23. Okay, what is that per mole? Okay, now in this case, if I ask you, okay, in this case, if I ask you what will be the value of KB, so you can actually calculate it. It will be 8.314 divided by 6.022 into 10 power minus 23. It somehow comes out to a value of 1.38 into 10 power minus 23. If you want to calculate, guys, you can. I would suggest don't. If I'm telling you something, मान लो कि मैं बोल रहा हूँ, I have never told you anything wrong, right? So yeah, मतलब I will at some point. I will, because even maybe बस I'm also a human being, so I will tell something which is wrong. But so far I'm not. This time I'm right. Okay, this time I'm right. So remember this. This is something called Boltzmann constant, and this we will use in some time. This we will use in some time. Okay. Now, if we have Boltzmann constant, then let's talk about law of equipartition of energy. What exactly is law of equipartition of energy? So, law of equipartition of energy, guys, the law actually states something like this: that for a dynamic system in thermal equilibrium, the total energy is equally distributed in all possible energy modes, and energy for each molecule, for each mode, is on average is on average half into kb into t per degree of freedom per molecule. Okay, what does this mean? What does this mean? So basically, guys, if you guys remember a monoatomic molecule, I told you that monoatomic molecule can move in three different directions. Okay, and can store energy by movement in three different directions, in x, y, and z. Okay, so it can move in this direction and can have kinetic energy due to that. It can move in this direction and can have kinetic energy due to that, and it can move in this direction, you can have kinetic energy due to that. What law of equipartition of energy says, that because of movement in x direction, its kinetic energy is going to be half into kb into t on an average. This is not for each molecules, guys. This is on an average. Similarly, if I take a molecule moving in y direction, its kinetic energy on an average is also going to be half into kb into t. And if it is moving in z direction, its kinetic energy is still going to be half into kb into t. Okay, here KB is what, by the way? KB is Boltzmann constant, and T is what? T is temperature in Kelvin. This is temperature in Kelvin. If I ask you what will be the total energy, what will be the total energy of one molecule? What will be the total energy of one molecule? You know what? I will write the entire thing here. One molecule. Okay, so total energy of one molecule, guys, will just be sum of all these three energies. It will be just sum of all these three energies, and that will be equal to 3 by 2 kBT. Okay, I hope everybody understood. Similarly, guys, if I have a diatomic molecule, if you remember, the degrees of freedom are equal to how much? It is 3 plus 2. 3 translational plus 2 rotational. Okay, so in this case, if I ask you what is the total energy of one molecule, what is the total energy of one molecule, then in that case the total energy of one molecule will be equal to 5 into half kBT. Why am I writing it as 5 into half kBT? Because for each degree of freedom, the energy will be half kBT. So if you have overall 5 degrees of freedom, the total energy will be 5 kBT. Or I can, अरे मैंने ये F क्यों लिखा इधर? F क्यों लिखा? F क्यों लिखा? The total energy will be equal to how much? The total energy of one molecule is going to be 5 kBT by 2. Okay, similarly, if I have a triatomic non-linear molecule, okay, if I have a triatomic non-linear molecule, one second, can I just make changes here? Uh, Triatomic non-linear molecule. Okay, then in that case, your F is just equal to, मैंने क्यों ये सब हटा दिया? Your F is just equal to 3 plus 3, 3 translational, 3 rotational, overall 6. Energy of one molecule is just going to be equal to half into kb into t times 6. I will just multiply with the number 6 and 6 here. Okay, it just becomes 3 kb. It just becomes 3 kb. I hope everybody understood. I hope everybody understood. Okay, really hope everybody understood. Everybody understood. Okay, then guys, we have something called vibrational degrees of freedom. Vibrational degrees of freedom. Okay, what exactly are vibrational degrees of freedom, and who do we talk about for vibrational degrees of freedom? I hope you guys will follow. First of all, when we talk about vibrational degrees of freedom, we are only talking about, remember this, we are only talking about a diatomic molecule, okay, or a triatomic linear molecule, or a triatomic linear molecule. Okay, we only talk vibrational degrees of freedom for these guys, because in other gases, first of all, monatomic gases, so it's just not possible. For triatomic non-linear molecules, it happens at very high temperature and it doesn't matter for us. And secondly, you only talk about this only comes into play at very high temperatures, where only comes into play at very high temperatures. Okay, so what exactly is vibrational degrees of freedom, guys? What happens is, if I have a diatomic molecule like this, if I have a diatomic molecule like this, you know what, I'm going to write it like this. Okay, let's say this is my diatomic molecule, and I will make the axis, the x-axis, the y-axis, the z-axis. Okay, in some cases at very high temperature, what happens is, like, these are the two molecules. Okay, look at me, look at me. I think you should look at me for this. Okay, let's say these are the two molecules and they have a fixed distance between each other. Okay, so basically you can imagine two molecules like this, they can move together like this and they can rotate or anything. Okay, this is one molecule and this is second molecule, but they can't move away from each other. But what happens is that at very high temperature, they also start, initially they were moving together, but at high temperatures, they also start vibrating with respect to each other. They also start vibrating with respect to each other. And when they vibrate, they all have extra degrees of freedom, extra ways to store energy. Okay, so what will that degree of freedom be? What will that degree of freedom be? So you have to remember here, guys, that when such a thing happens, let me remove this first of all. Okay, when such a thing happens, the number of degrees of freedom is going to be, number of degrees of freedom is going to be 3 translational, okay, plus 2 rotational, plus plus 2 vibration, 2 vibration. Okay, why 2 vibrational? Why 2 vibrational? Because whenever something is vibrating, it has vibrational kinetic energy, vibrational kinetic energy, and it also has vibrational potential energy. Okay, so there are two different ways in which you can store energy if you are vibrating in the form of kinetic energy or in the form of potential energy. Okay, and in such cases, this by the way is not happening at normal temperatures. This by the way is happening at what? It is happening at high temperatures. Okay, it's happening at high temperatures. Okay, at high temperatures, what will happen is number of degrees of freedom will be 7, and therefore energy of one molecule, if I ask you guys what will be energy of one molecule, what will it be? What will it be? 7 by 2 into kb into 7 by 2 into kb into t. I hope. Yeah, there is Ritik. You know what you can do, Ritik? What you can do is you can use Google Drive. Do you know Google Drive? You can use that as well. Okay. I hope everybody understood, guys. I really hope everybody understood so far, and it is important that you guys understand. Okay. Now, based on this, guys, we have a next topic, and we will talk about this topic again in case of we'll talk about this topic again in case of thermodynamics as well, but for now we will give it one shot here. Okay, and that topic is called internal energy of a gas. Okay, now, when I'm writing these, I'm talking about, by the way, ideal gas. Okay, whatever gas we talked about, hydrogen, oxygen, nitrogen, helium, neon, argon, whatever. Okay, we are considering all those gases right now as ideal gases. Okay, when we consider them as ideal gases, they only have kinetic energy. They don't have forces of attraction between the molecules, and we can ignore the energy due to that. I'm only talking about ideal behavior of all those gases. Okay, now in such cases अच्छा पानी पी लो, it is distracting. Okay, पानी पी लेता हूँ, ठीक है. So in case of ideal gases, I know that the total energy of one molecule, the total energy of one molecule is going to be equal to how much? That is going to be half into kb into t. Now, if I have a container, guys, if I have a container with gas inside it, okay, with gas molecules inside that container, then I'm not going to have one molecule. Wait, 1 second. First of all, I wrote this as wrong. Energy of one molecule in general is going to be F by 2 into kb. Okay, why F by 2? Why F by 2? Why F by 2? Because I hope everybody understood why F by 2. Why F by 2? Because we have F degrees of freedom. So for 1 degree of freedom, it's half kbt. Okay, anyways, if I have molecules, then I won't have just one molecule inside. I will have many different molecules, guys. Let's say all these molecules are moving in random directions. Let's say inside I have a total n molecules, okay, and n moles. I have n molecules and n moles. I hope everybody understood. I hope everybody understood. By the way, if I ask you what is the relation between this n and n, can you tell me the relation between n and n? Number of moles will be equal to how much? Number of moles will be equal to number of molecules divided by number of molecules divided by Avogadro's number. Number of molecules divided by Avogadro's number. I hope every guys understood. Okay. Okay, all right. Next is, if you understood so far, let's go one step further. If I ask you what is the total internal energy, if I ask you what is the total internal energy, I'm going to denote that total internal energy as U. If I ask you what is the total internal energy of this gas, total not internal energy of this gas, can you guys tell me what will be the total internal energy? Can you guys tell me what will be the total internal energy? The total internal energy will be equal to number of molecules into energy of one molecule. The total internal energy will be equal to number of molecules into energy of one molecule. So I hope everybody understood this, guys. I really hope everybody understood. Why? One molecule has F by 2 kBT energy multiplied by n molecules, because we have n molecules, so I'll get the total energy. I hope everybody understood so far. Okay, really hopes, really hopes. Okay, now if I know this, I will just substitute the values. I will just substitute the values. So I will get U is equal to N into F by 2 into KB into T. I don't like this formula in terms of, I don't like this formula in terms of what? In terms of this number of molecules. In general, we know number of moles. So let's try to talk in terms of number of moles. So what will be the formula in terms of number of moles? In order to do that, let's write the value of Kb as R divided by Na into T. Now, if you replace this, if you displace this a little bit, you can write this as F by 2 into N upon Na into R into T. Okay, which gives me what, guys? Which gives me U is equal to F by 2 into N into R into T, because N by Na is equal to number of moles. I hope everybody understood. I hope everybody understood. This is the very important formula. यस आयुष ये फॉर्मूला याद करने के लिए एक ही तरीका है टेबल बनाओ ठीक है एट द एंड ऑफ थर्मोडायनेमिक्स विल मेक दैट टेबल एंड यू विल अंडरस्टैंड ऑल द फॉर्मूलास डू नॉट वरी ओके एट द एंड ऑफ thermodynamics will make that table and you will understand all the formulas, do not worry. Okay, so guys, you have to remember so far that I have, when it comes to internal energy, I have two different formulas. Okay, the first formula is energy of one molecule. Okay, that is F by 2 into Kb into T. Okay, but if I ask you energy of n moles, then you have to use the total internal energy, then you have to use F by 2 into N into R into T. I hope everybody understood. You will need to remember both these formulas. You will need to remember both these formulas. Now, someone might be asking, sir, where does this law come from? ये तो मैं आपने explain ही नहीं किया, sir. You did not even explain. Where does this law come from? Okay, so this law is just, you just understand that this is based on empirical evidence. So okay, it has a theoretical proof, but you just remember for now that this is based on experiments. Okay, there's no proof for it right now for you guys. So right now just assume that if I'm saying it correct. Okay, even though there is a proof for this law, right now we can't do that. So just assume that it's based on experiments. Assume that it's based on experiments. It's based on experiments. I hope everybody understood. Arey, no, Rakuti, Nitin, I can't tell you the proof. Now, even if I want to, I can't tell you the proof, my friend. So, no. If I tell you the proof, everybody will run away. Hi, Lavanya. Okay, Varun Shastri SAT tips definitely in the next class. Okay, I definitely in the next class. So, anyways, next topic, guys, is called specific heat capacity of gases. Specific heat capacity of gases. Now, guys, you have to understand that when we talk about solids, let's say I have a solid body of mass m. Now you guys know that if I give it some heat, what will happen is that its temperature will change. If I give it some heat, its temperature will change. And I know that the amount of heat given is directly proportional to the change in temperature. The more temperature change I want, the more heat I will need to give. Similarly, the amount of heat required is also directly proportional to mass. The bigger my mass is, the more heat I will need to give. If I combine both of them, I will just write a delta Q is proportional to m delta T. And if I remove the proportionality, I just write delta Q is equal to mc delta T. This C is called what? This C is called specific heat capacity. Specific heat capacity. I hope everybody knows this. I hope everybody remembers so far. This is just revision of what we have done in the last chapter. Okay, like what we have done a few days ago. Now, here, this is by the way called a gram specific heat capacity. This is called gram specific heat capacity. Here, let's assume that the number of moles here is equal to n. Number of moles is equal to n. So if I ask you what is the relation between n and m, so you can write number of moles is equal to mass upon molar mass. Here you have to remember number n is what? N is equal to number of moles and m is molar mass. If you have studied the mole chapter in chemistry, you will understand this formula. Okay, if you haven't studied, then you are in the wrong class, my friend. Okay, anyways, so from this I can also say, by the way, I can also say that delta q is proportional to delta t, but it is also proportional. Delta q is also proportional to, if instead of mass I talk about number of moles, I can write that delta q is also proportional to number of moles. If I combine both of them, this is proportional to n delta t, proportionality removed, I will get it as n c delta t. Here's capital C, this is capital C. Okay, this is called molar specific heat capacity. Molar specific heat capacity. Okay, this is what we say. Now, in the last class when we talked about it, and this formula becomes very important here. Okay, so the last time when we talked about it, we also calculated the relation between capital C and small c. I don't know if you guys know this, but capital C is equal to small c into m. Capital C is equal to small c into m. Okay, is that correct? By the way, is that correct? Am I doing it correctly? Yes. No. I don't know. Is it capital C into m or divided by m? Oh my God, I am so confused. I hope a student can tell me the correct answer. Okay. Alright, I guess nobody is going to tell me the correct answer. It's okay, guys. It's okay. Let's move on. Okay, it's okay. It's okay. I understand. Okay, now this was for solids. Okay, solids and in general liquids as well. But guys, when it comes to gases, okay, you have to remember that we generally only talk about molar specific heats. Okay, we generally only talk about molar specific heats. Okay, what do I mean by only generally talk about molar specific heats? Basically, we do gram specific heats we can calculate, but we generally don't talk about that. We generally talk about capital C. We generally talk about, it's not looking like capital C, capital C. Okay, generally only talk about capital C. And secondly, the value of capital C, depends on, the value of capital C depends on, this is very important, remember this, the type of process. Now, guys, all these things we are going to study in much greater detail when we study the next chapter called thermodynamics. Okay, but right now I'm introducing you to this, and right now I'm just giving you the formulas, and you just have to remember all the formulas. Okay, right now I'm not explaining the formulas. The formulas that I will give we will derive later, but for now I'm just explaining you the formulas. Okay, and when we talk about the specific heat, it depends on the type of process. There are two special processes that we will talk about. Okay, there are two special processes that we are going to talk about. It's called isobaric process, okay, or isochoric process. There are two special processes that we are going to talk about. Now, if you have studied chemistry, you know what these processes are. Okay, isobaric, by the way, I will represent with iso P. Okay, and isochoric I will represent with iso V. Okay, what is iso P and iso V, guys? It's a process. Isochoric process is a process in which no matter how much I heat the gas, no matter how much I heat the gas, its volume remains constant. Okay, volume remains same on heating the gas. Okay, now how do we achieve this, guys? How do we achieve constant volume on heating the gas? By using an appropriate container. If I use a container like this, if I use a container like this container is closed in all directions, and if I have gas inside this container, when I heat this gas, as you can see, the volume of this gas will not change and the volume will remain constant. Okay, because the gas has no space to expand. This is called isochoric heating. This is called isochoric heating. Now, the value of a specific heat capacity of the gas in this case is called CV. The value of specific heat capacity of the gas in this case is called CV. Okay, similarly, if I'm heating a gas in an isochoric process, how will that look like? How isobaric process, how will that look like? So imagine I have a container, okay, and this container has a piston here, okay. This container has a movable piston here, which can move up and down, okay, and that piston has area A, and on top of it, I keep a mass M. Okay, now in this case, guys, if I heat this gas, what will happen is that the piston will start moving up. In this case, if I heat this gas, the piston will start moving up, but the pressure here will remain constant. Here, the volume remains constant. Here, the pressure remains constant. Okay, I hope everybody understood. Okay, now in this case, the specific heat capacity of the gas is called Cp. In this case, the specific heat capacity of the gas is called Cp. I hope everybody understood. Now, right now, there are derivations for Cp and Cv, guys. Okay, there are derivations of Cp and Cv, and we will talk about it later, but not right now. Those derivations will do after thermodynamics, at the end of thermodynamics, rather. Right now, let me just give you the value of Cp and Cv. Let me just give you the value of Cp and Cv. And you have to just remember the formula. By the way, which type of heat capacities are there? Gram specific heat capacities or molar specific heat capacities? These are molar specific heat capacities. Okay. So the value of Cp, guys, for any gas is equal to F by 2 plus 1 into R. F by 2 plus 1 into R. Now, what is F here? F is the number of degrees of freedom, and R is 8.314, the universal gas constant, joule per mole per Kelvin. Don't make me write यार एक बार एक आदमी को डांट दो. If I tell you that units are important, okay, so that doesn't mean that every time you make me write the units. Okay, let me go sometime. Let me go. I'm not going to write the unit next time. Okay, similarly, CV has a formula F by 2 into R. Now, guys, you have to just remember the formula. Right now, I'm just giving you the formula without derivation, and just please remember the formula. We will do the derivation in thermodynamics. We will do the derivation in thermodynamics. Right now, just remember the formula. Both are molar specific heat capacities. Both are molar specific heat capacities. Okay. By the way, if this is the formula for both of them, guys, if this is the formula for both of them, then I have a very simple question to ask you. If these are the formulas for both of them, then can you tell me what is the value of a Cp minus a Cv? Can you tell me what is the value of a Cp minus a Cv? What is the value of Cp minus Cv? What is the value of Cp minus Cv? Oh, everybody. Yeah, the value of Cp minus Cv is R. Okay, now here we have also one more very important quantity. It's called a ratio of specific heats. It's called a ratio of specific heats. Okay, what exactly is ratio of specific heats? It's called gamma. Okay, and the formula for gamma is Cp divided by Cv. Formula for gamma is Cp divided by Cv. Now if you do all this calculation, it will be F by 2 plus 1 into R divided by F by 2 into R. Okay, and if you do this calculation a little bit more, guys, if you do this calculation a little bit more, this will just come out as, no, let's not do this. This will just become 1 plus 2 by F. Okay, this will just become 1 plus 2 by F. You can do the calculation and check it yourself. Calculation, if I tell you it's correct, guys. If I tell you it's correct. Okay, if I tell you it's correct. So that is the formula for Cp, Cv and gamma. Gamma is once again very important quantity, guys, and you will need to remember this. Now, this is the problem with thermodynamics. See, there are so many different quantities and it becomes very hard to keep a track of them and to keep understand them physically. And I understand it's like the physical significance of velocity everybody understands. Okay, everybody understands what is velocity, everybody understands what is force, everybody feels of force when we do this, but like it's very hard to understand what is the physical significance of gamma and why are we even talking about gamma. I understand, don't get into that. Okay, do not get into that. Just learn this formula and solve this question and move on to understand thermodynamics at that physical significance wala level. You will need to study a lot of it, which is not going to happen in class 11th and 12th. Just remember this and this formula for now. Okay, by the way, this formula has a special name. It's called Mayer's formula. Cp minus Cv is equal to R has a special name. It's called Mayer's formula. Okay. I hope everybody understood so far. I hope everybody understood so far. Now, guys, before I tell you the next thing, let's talk for 2 minutes about Vedantu's JEE and NEET platform. If you're preparing for JEE and NEET 2021, 2022, Vedantu's platform is just for you guys. You get full access to all the live courses where all the subjects are covered in great detail. You get to choose the language in which you want to study, English or Hindi. Okay, and you get instant in-class doubt solving where there are class teachers and master teachers. There are going to be class teachers in the class who are there just to solve your doubts. Okay, and how many doubts can you ask, by the way, in a class? Infinite number of doubts. It becomes very convenient to be able to ask a doubt during the class. Okay, also at the same time you get to study from India's best teacher, all of them having more than 5 years of teaching experience, and you get to study from your home on any device. Now there was a special offer till yesterday where you used to get 30% discount. That has ended now, guys, but we still have 15% discount. If you go to this link vdnt.in/ytpro and use my coupon code AAPPRO, you will get 15% discount on the price. You will get 15% discount on the price. Also at the same time, if you haven't joined our Telegram group, join our Telegram group. I will share the notes of this lecture and other lectures on that group. Okay, now coming back to this again, where is it, yeah, coming back to this again. So using this, I want to do what? I want to make a table. Okay, because I love making tables. Okay, tables are like my favorite thing, guys. Tables are like my favorite thing. Okay, especially in this chapter, tables are like so. I am just so into tables, guys. I am just so into tables, you don't even know. Okay, so let's say I have three different types of gases: monoatomic, diatomic, and triatomic. If I ask you what is the degree of freedom for each of them, it is 3, 5, and 6. Okay, if I ask you what is the Cp value for all of them, so Cp formula is equal to what? F by 2 plus 1 into R, and Cv formula is F by 2 into R. So substitute both these formula, find the value of Cp and Cv, and find the value of gamma. And when you do that, this is your homework. Okay, this is your homework. Complete this table in your homework and write down this value in comments. Write down this value in comments. Whoever gives me the first correct answer, I will take his name in the next class. Okay, that person goes to Hall of Fame. Right now it's probably, I know who's probably going to be, but ठीक है. खुशी श्रीवास्तव is asking, सर आप बोर्ड पर कब पढ़ाएंगे? खुशी कभी तो आएगा बोर्ड, डोंट वरी अबाउट बोर्ड राइट नाउ. ओके, अभी के लिए मैं इसी पे पढ़ाएगा, but the good thing is I will share the notes, so do not worry about it. All right guys, so that is it for today's class, guys. That is it for today's class. If you have any doubts, okay, some students have been doing this. If you have any doubts, you can ask me your doubts on Telegram. Okay, at AADITYAP 832. But guys, remember, because I get a lot of doubts, so sometimes it will take me a time to get back to you, but I do get back to you. Okay, I have gotten back to Entertainment 2015. I have gotten back to on Thayar. I got back to a lot of people. Okay, so I do get back to you. If you have any doubts, you can send it to me on this. I will try to get back to you as soon as possible. Okay. Anyways, so this is the end for today's class, guys. Tell me, how did you like it? Oh my god. Tell me how you liked it. Okay. Tell me how you like my new setup. You like this new room? Is there anything behind me? Is there anything moving? Is there coming to attack me? You can tell me anything in the comments below. Okay. If you have any suggestions, you can write them in the comments below. And also at the same time, I will see you guys now next on Tuesday. We will continue with this chapter. We will start the last topic of heat and temperature, that is thermodynamics. Okay, it's going to be a fun, well, it's going to be a formula intensive chapter. Okay, but it's a scoring chapter, because if you remember the formulas, if you know how to apply those formulas, you can get marks very easily. Okay, so that is it, guys. We will stop here. We will stop here. I'll see you guys in the next class. Okay, bye bye. Bye bye. Have a nice day, everybody. Bye.